Hi. So today in this video, we're gonna continue our discussion on the sets. Okay, and we're gonna introduce the closed set and later also introduce the notation for the sequence and the limit. Okay, so we say that a set S in as a subset of the n-dimensional Euclidean space. So we're gonna say this S is closed if the complement of S is open. Okay, so for example, in the one dimension real line, if we're gonna say that those two dots to the left and then to the right, not including those two dots, so their union will be an open set. Okay, so the complement of that set on this real line, that'll be this part, right, including those two bounds. So that'll be the complement of the open set. So this would be a closed set. Okay, so we have very similar properties that we saw before when we introduced the open sets. Okay, so the first is that the empty and the Euclidean space itself, they're closed. Okay, and remember that we said that those are open, right? So now we're gonna say that those are closed as well. Okay, so the second is that the intersection of any closed sets, it is closed, and the union of any finite number or finite collection of the closed sets is closed. Okay, so for all those three properties, that we're gonna prove those using just the results that we obtain from the open sets. Okay, so the first, that will be very straightforward. So we're just following the definition of the closed sets, that would be the complement of the open sets. So we have known that the Rn and empty set themselves, they are open, right? So their complements, they're just closed. And second, we want to show that the intersection of any closed sets, we didn't say it's infinite or finite, right? So it could be infinite, right? So here we're gonna say that this intersection of any closed sets is closed. So let's consider a set as alpha that is closed for all the alpha. Okay, so and this alpha, that could be from 1 to up to infinity. Okay, so it doesn't matter. And then we want to show that the intersection of all those S alphas, it is closed. Okay, so here when we're trying to show those properties that we're going to have those multiple unions or multiple intersections, we're going to always use the De Morgan's law, right, to deal with the union and the intersections with those complements, right? Okay, so we're going to have this complement of the intersection of S alphas. So by the De Morgan's law, so what we have is to first to take the complement of each S alpha and then take the union instead, right? So that's just strictly following the De Morgan's law. And then we know that inside of this, so S alpha, we said that this is closed, right? So the complement is open, and then the union is open, and of course the complement of that will be closed. Okay, so that's the second. And for the third, and we just again follow the result that we obtained from the open sets and also following the De Morgan's law. So now I'm going to consider this set Si to be closed, and here we have to assume we have to restrict that those little i's to be finite from 1 to up to n. Okay, so this n has to be a finite, which is less than infinity. Okay, so we want to show that this union from n1 to n, so for Si set, that will be closed. Okay, so we're gonna again to use the De Morgan's law and to take the complement of this thing, and that gives us the intersection instead, right? So, and that would be the intersection of all those SI complements. And we know that this SI is closed by that's our starting point, right? So the complement is open. So then we, from the open sets results, we have this intersection with finite number of those that will be open, and so the complement that will be closed. Okay, good. So and here we have this finite restriction, right? Exactly the same as before when we introduced the open sets. So again, we're gonna also, it's also possible for us to have another example to show that sometimes if you have infinite number of or infinite collection of closed sets, so that's union, it might not be closed. So we have this SI defined including the boundaries, okay, and that would be this 1 over I and 1 minus 1 over I. Okay, so I is 1 to up to infinity. So if we take the union from 1 to infinity for the set Si, so that has to be the open set from 0 to 1. Okay, and it's easy to show that all those numbers in between, they're included, but the boundaries 0 or 1 is not included. Okay, so here the key point is that the 1 over I and 1 over 1 minus 1 over I. So we, by the construction, we have those 2 points included in the set. Okay, but be careful that when we're taking the limit or when we are approaching the limit that from I goes from 1 to infinity. So here it doesn't go. So if it goes to infinity, but we're gonna have this boundary included, okay, but that cannot be reached actually, right? So this means that we cannot have those limits included in this union, right? So here we have this open set to be this union, okay? So that would be a example if we have this infinity here, right? So that's why we have the finite assumption here. Good. So the second thing for today, we're going to introduce the definition for the sequence. Okay, so again, in the n-dimensional Euclidean space, so a sequence, that would be just an infinite ordered list. Okay, you can call that as a list or just a series, right? But normally we do not need to really strictly give some name for that. Okay, we just know the definition, we just know the meaning of that. That'll be enough, right? So that'll be written, if I write some sequence, you can write this xi, okay, and we have this curly brackets around this xi and have a subscript and superscript from 1 to infinity. Okay, and we mentioned that this has to be an infinite list, right? So this is also ordered, okay, and this xi, that would be an element in this Euclidean space, okay, from 1 to up to infinity. All right, so as an example, here we have this real line in R1. So this could be x1, right, and this could be x2, x3, so on and so forth, and it goes to somewhere on this real line, but there are infinite number of those points. Okay, so this is an ordered list as a sequence. Okay, all right. So then we're gonna talk about the convergence. Okay, so this is a definition based on the sequence. So we say that a sequence, this xi from 1 to infinity in Rn, that converges to this x. Okay, so this x is a point, and we're going to call this x as the limit. Okay, so it converges to this x if for all the epsilon greater than 0, there exists some number capital N such that the subscript I, is greater than or equal to n, and we have the Euclidean distance between the xi and this point x smaller than this epsilon. Okay, and then we call this x to be the limit of the sequence. Okay, so intuitively it is easy to understand, right? But for the definition, it seems pretty not straightforward, right? So here we use this little figure to show some intuitions or some explanations of this. Okay, so here we have, again, on the real line, we have this sequence goes starting from somewhere else and then goes from here, and the distance between the each two dots, they decrease again and again, and finally it converges to some point. Let's say it converges to this limit. Okay, so this x point. So we say that in the definition of this convergence, we say that no matter how small this epsilon ball is, okay, we just draw a circle or a ball, epsilon ball with the radius epsilon, we can always find some points, actually infinite number of points inside of the ball, right? If we have this ball just around this limit point x, right? So it means that around this limit point x, there are always infinite number of those points converging to this limit, right? So it means that no matter how we draw this epsilon ball, we can always find infinitely many of those points around this x, okay? And that is very straightforward, right? For example, if we're gonna draw some ball around some other points, then we might just see one point here, but if we draw a ball here, then maybe there is actually no point, right? So that's why this point is defined as the limit of the convergence. Okay, good. So that's the second thing that we talked about today. So the third and last thing for today, that'd be the notation for the bounded set. Okay, so we say that a set as a subset of Rn that is bounded, okay, if there exists an epsilon such that this S is a subset of this epsilon ball, and with radius of epsilon and with the center of 0, the origin. Okay, so this is just a canonical or convenient notation, right? You can change this 0 to any other points as long as we just have some epsilon ball and this set is included inside of this epsilon ball. Okay, so then we can say that this is bounded. So this simply means that, for example, here in this little picture, we have this epsilon ball, and that's an epsilon open ball, right? And that is including this set S. S is included in this epsilon ball. So here something important to notice is that the difference between the boundedness and the other notations that we have seen before, right? So, and later in the future episodes, we're gonna talk about the relationships between the bounded set, and also talk about the convergence of a sequence. Okay, so we're gonna link all those together. But for now, it's enough for us to notice the difference between the boundedness and the open and closed sets, right? So that'll be enough for now. Okay, good. So that'll be everything for today.